Hi everyone, I'm Nora, and today I'm gonna present my Math 40 final project, which is a topic of Monte Carlo simulation of option pricing based on the Black-Scholes module. The original Black-Scholes paper from 1973 developed one of the most important mathematical methods in finance. It assumed that the stock price follow a continuous time random process, and under this assumption, the author derived a closed-form formula for European option price. This module becomes the fundamental of the module, modern quantitative finance, and it is still used on trading desk and risk management. In this project, I focus on three questions. First, can we reproduce the Black-Scholes theoretical price using Monte Carlo simulation? Second is, how does the volatility affect the price of the European call option? And the last is, how close is the simulation result to the theoretical formula? Option pricing matters because options are everywhere in finance market and they are used for hedging and risk management. Banks, hedge funds, and trading desks rely heavily on accurate pricing module to avoid arbitrage and to manage risk. Black-Scholes remain one of the most influential module because it provides a clean mathematical benchmark for value. To module option price, we first need to module how the underlying stock behaves. The Black-Scholes assume that the stock follows the stochastic differential equation, which is ds equal to mu s dt plus sigma s dwt. And this assumption is what allows us to derive option price mathematically. By solving the stochastic differential equation, we get a expression for the future stock price, which is the ST equal to S0 times the E to the power of those kind of things. And this tell us the stock price is log normally distributed, and also this distribution allows us to compute the probability and expected payoff, which are essential for valuing the option. A European call option pays the amount of the maximize of minus t or zero at the maturity. So if the stock price ended above the strike price K, the option has value. If it ends below the strike price, the payoff is zero. So the fair option price today is simply the discounted expected value of this payoff under the module. To approximate the price, I use a Monte Carlo simulation. So this idea is really simple. There are four steps. Simulate many future stock price, which is ST, and compute the payoff of each simulated path. Then take the average of the payoff. Finally, is just discounted the result to the present value. So with enough simulations, the law of the large number guarantee that the numerical price will coverage the true theoretical value. So for my simulation, I use standard benchmark parameter. Initial stop price for 100, strike price 100, risk-free rate for 5%, volatility for 20%, and maturity is 1 year, and the number of simulated passes 10,000. Here I will show the simulated stock price path generated in Python. Each line represents one possible future path of the stock under the this motion, which is the assumption behind the Black-Scholes module. And the spread of this path illustrates the randomness and uncertainty in stock movements. Later, I use those simulated end price and to compute the average discounted payoff of option, which gives the Monte Carlo estimate. So we can see that in my Python code, I simulate stock price using this motion formula, then compute the payoff for each simulated path. After discounting the average of this payoff, I obtain the Monte Carlo estimate for the option price. So yeah, so this is my full like coding process of it, and so we got the graph here. So this plot shows that how the option price change when volatility varies. So the blue line is the theoretical black Scots price, and the orange dot are the Monte Carlo estimate. We can see that a very clean upward trend as volatility increase the value of call option risk, and this happened because higher volatility increased the probability that the stop price and above the strike price. And also the Monte Carlo result match the theoretical curve closely, and which confirms that the simulation is accurate. To conclude, the Monte Carlo simulation successfully reproduced the Black-Scholes price, confirming that the mathematical result in the original paper. We also saw that the volatility has a strong positive impact on option values. So, overall, this project illustrate how theoretical module and computational method can work together to help us understand the real-world finance instrument. Of course, the Black Scotch module has some limitations. It's like assume the constant volatility and no transaction cost and continuous trading. Um, and we all know in real market, it often violates those assumptions, which is why more advanced module continue to be developed. But despite these limitations, the Black Scotch remains an essential tool in the finance world. So that is what I'm gonna share today. Thanks so much.